everyone, today we are going to derive the equation of centripetal acceleration, which is centripetal acceleration equals tangential velocity square by r, AC equals Vt square by r. So to derive this, at first we are going to consider the circular motion, and let's suppose this is the center, and if at a time t1, let's suppose this is the position of the particle. I mean, here there was a string, and let's suppose a stone was connected to it and it was moving in circular motion. I mean, we are rotating it. So at time t1, this is the position, and after some time, let's suppose it is at time t2, the position is this. So represent this position with r2 bar, and time is t2, and assume that it moved through a angular displacement of theta, right? It rotated through an angle of theta in this time of delta t. Delta t is t2 minus t1, right? And here we can consider one more vector, which is the change in displacement vector. Delta r vector, right? So some basic vector rules, we can say that r1 bar plus delta r bar equals r2 bar, right? So that makes delta r equals delta r2 bar minus delta r1 bar, right? But a thing to remember, the modulus of r1, r2 is the same, r, because the radius of circular motion isn't going to change, right? It is uniform circular motion, right? So this is one condition. And now what other vector we can consider? Velocity vectors. So again, draw the same circular motion, but now we are gonna do the same thing for velocity vectors. So this is the initial position, so the tangential velocity is gonna be in this direction. Let's suppose it is v1, and after some time this is the position, and it is gonna be in this direction, right? So we know that the velocities are perpendicular to the displacement vectors, because it is tangential velocity, right? The displacement was along this line and the tangential velocity was perpendicular. So this delta r, change in displacement, was in this direction, so we can directly say this is going to be perpendicular. I mean, change in velocity vector is going to be perpendicular to this, so it is going to point towards the center. So neatly drawing these vectors, this is going to be v2, this is going to be v1, and this is going to be theta, because as these were perpendiculars, I mean displacement and velocity were perpendicular, right? So this angle is still going to be theta, and the change in velocity vector is going to point in this direction. So sorry, I did a mistake. v1 bar should be in this direction and v2 bar should be in this direction. Sorry, I mean it is moving in clockwise, right? So as it is moving, the velocity vector will move like this, right? Again it is going to change, what though? So v1 bar plus delta v bar equals v2 bar. Similarly, delta v bar is equals to v2 bar minus v1 bar, and modulus of delta v1 bar equals to modulus of delta v2 bar equals to tangential velocity, right? And we can observe that this and this are similar triangles, as the angle was same. So we can take delta v by modulus of any of these, which is equals to tangential velocity, equals to delta r by modulus of any of these, equals to I mean we are going to equate these, because these were similar triangles, right? Using similar triangles concept. So delta v equals delta r by r times vt. So we can divide with delta t on both sides, right? So delta v by delta t equals to delta r by delta t into vt by r. So as generally change in velocity by change in time was acceleration, right? Here it was centripetal acceleration, right? So I mean as this was in this direction, right? Here drawing wasn't proper, so it was looking like that, but in reality it looks like this. So it points towards the center. So centripetal acceleration equals to, and this was average velocity, right? Which was just tangential velocity. So tangential velocity times tangential velocity equals tangential velocity square, and this was r. So hence proved centripetal acceleration equals vt square by r.